UCLA, Professor Ozcan, Selvin, and then I'm going to tell you a little bit about our research. So let me first welcome Professor Aydogan from Electrical Engineering at UCLA. He's going to talk about computational microscopy, sensing, and diagnostics. And I want to give you a little bit of his biography. He received his PhD at Stanford, and then he joined the Bellman Center for Computational in 2006, and joined UCLA in the summer of 2007 as assistant professor on the tenure track, and became associate and full professor in 2011 and 13 respectively. And currently he's the Chancellor's Professor at UCLA, leading the Bio and Nanophotonics Lab in the Electrical Engineering and Bioengineering Department. He's also the Associate Director of the California Nanosystems Institute at UCLA. There's a long list of awards that Professor Ozcan won, probably all of them. So let me list a few of them. So Dr. Ozcan received the 2013 SPI Biophotonics Technology Innovator Award, the 2011 Army Research Office Young Investigator Award, 2011 SPI Early Career Achievement Award, 2010 NSF Career Award, 2009 NIH Director's New Innovator Award, 2009 Office of Naval Research Grant, again Young Investigator Award, 2009 IEEE Photonic Society Young Investigator Award, the MIT Technology Review PR35 Award, for his seminal contributions to near-field and on-chip imaging and telemedicine-based diagnostics. The list goes on and on, but I guess I will stop right here. So it's a great pleasure to have Professor Ozcan. Thank you so much for taking the trip.
Thanks. Thank you. It's a great pleasure to be here. My first time at Urbana-Champaign, so also very happy to see this nice campus at the right time of the year. And thanks for the invitation. Thanks. So. I'll today talk about some of our work on the use of computation. So essentially we try to use computation for simplification of imaging systems to create new kinds of microscopes and sensors and diagnostic tools. The emphasis in terms of the application domain is mostly telemedicine, mobile health, point of care medicine, as well as global health. And I'd like to start my presentation actually with this slide, which compares Moore's law with the megapixel count of cell phones that we've been experiencing rapid growth. I'd like to start with this one because it tells how important mobile phones, smartphones, are for especially conducting scientific imaging experiments. What you see here with the blue dots is the standard Moore's law, which is doubling of transistors every 2 years in our CPUs. What is new here is essentially the megapixel count of cell phones with the red dots, which also doubles every 2 years for the last 10 years or so. Now it has reached to more than 40 megapixels with some new generations of smartphones. This is not expected, this kind of a rapid growth in terms of the megapixel count in CMOS sensors that are installed at the back of our cell phones. This is surprising, but it is our bread and butter in a sense, because now we have at our disposal very inexpensive, compact, and cost-effective digital imaging systems that can even have 40 megapixels at the back of our smartphone. So this is something I'd like to emphasize because it's helping us a lot, and I'll show you some examples of what we've been doing with some of these sensors. Just to give you a simple result that I'll later on show and share with you is with some of these recent sensors you can, for example, see individual viruses using your cell phone. So you can convert your cell phone into a viral load measurement tool at the single particle, nanoparticle, or virus level. In addition to this, smartphones are also special because they're also supercomputers. They are better in terms of their computational power than some of the supercomputers of IBM in early 90s. And as you can see with this plot, mobile phone clock rates are now almost on par with PCs. So in our pockets, in addition to advanced optoelectronics, we also carry supercomputers so that you can have computational imaging from the raw CMOS data to the image reconstruction be achieved there using even graphics processing units that are now appearing in our cell phones. And in addition to all of that, in terms of hardware and software, we also have a massive volume around mobile phones. We have now around 7 billion cell phone subscribers, sold more than 15 billion cell phones so far. All of those large numbers of subscribers help us to drive the costs to almost nothing for a smartphone, despite the magnificent infrastructure that we have around the mobile phone. And more than 70% of these cell phones are being used in developing parts of the world. So it's a huge infrastructure where you can tap into and convert that into something more useful, especially for biomedical imaging and sensing applications. That's the research theme in our lab. And we essentially convert the cell phone into new kinds of instruments where, for example, you can conduct bright field or fluorescent microscopy. Again, these are, relatively speaking, older generations of phones, but with the Moore's law helping us, today you can routinely see single virus level details using some of these attachments to the phone. In addition to modifying your cell phone to convert it into a microscope, if you like, you can create standalone devices, which I'll present and discuss in this presentation, using the same components that you have around the cell phone. Using the CMOS imager of cell phones, you can actually create some of these field portable microscopes that are rather advanced in terms of resolution, field of view. For example, one of these field portable microscopes could generate 1 billion pixels, a gigapixel, across a very large field of view with almost diffraction limited resolution. In addition to microscopy, you can also do sensing with mobile phones. For example, this is a urinary albumin tester. It has an optical instrument at the back, an imaging system, and an Android application which can sense albumin in urine specimen with around a few parts per million level of sensitivity. And in this next slide, I'm showing some other instruments, like a blood analyzer, which can count, based on imaging, bright field and fluorescence microscopy, the count of red blood cells, white blood cells, as well as hemoglobin density in human blood, with just less than a few minutes of total imaging time. And also the processing is done here on the cell phone. And I've shown here some other examples. This is a recent work which we've used nanoparticle-based scattering to quantify mercury concentration in water samples. This is an interesting one because it has reached a sensitivity level on the order of 3 to 4 nanograms per mil. So you can understand that these levels are really very advanced. So this entire infrastructure with the cell phone and some of the emerging variable computers like Google Glass, which also can be used for biomedical sensing, as we've shown recently, all of this forms a network, an infrastructure that you can bring some of the advanced functions that you normally find in hospitals or advanced laboratory settings to field conditions, to remote locations through the cell phone and the connectivity of the cell phone. So in that regard, this is kind of important for, again, telemedicine, mobile health applications because of the cost effectiveness, compactness, and lightweight of these biomedical measurement tools. In addition to that, in addition to the individual element, individual sensor, there's also the network aspect of things because essentially you're looking at a large-scale experiment, so to speak, where because of this distributed network of measurement tools working wherever the cell phones work, you can actually accumulate a huge amount of data, which is also quite important because it can be used for looking at spatiotemporal maps of, for example, how diseases are spreading. So it's a great epidemiology tool as well, because now you will be able to extract at the micro and nanoscale information from wherever these cell phones or tablet PCs or smart watches or smart goggles are working. You can extract now specific, sensitive, and meaningful data at the micro and nanoscale. I think this is also a great opportunity, at the same time a challenge. If I have time, I'll expand on this direction a bit more, the big data problem or big data opportunity here, and give you some examples of what we've done around that. So if I have time at the end, I'll come back to this slide. So let's now come back to imaging, and I'd like to discuss some of these microscopes that are installed on cell phones, and I'll share how they work. I'll discuss how they work. First of all, these microscopes, as you can see, are very compact and lightweight. For example, this microscope is less than 50 grams, and this one is less than around 200 grams. And the attachments to the cell phone are typically less than 50 grams to convert the phone into a computational imager. The underlying formalism or the mechanism for these microscopes is a little bit different than traditional microscopes, and they're based on actually digital holography. They are lens-free microscopes on a chip, where the most important component is the CMOS imager. Whatever imager you have at the back of your cell phones, like 5 megapixel, 10 megapixel, that is the most essential part of these microscopes. They're lens-free on a chip, meaning the specimen is placed right on the top of that CMOS imager. That's the reason why you can build such a compact microscope, because there's nothing inside except a simple light-emitting diode or a light source and a CMOS imager powered by a USB here. Same here. And in these examples, it's actually using the CMOS of the cell phone. As a result of that lens-free operation, you actually have, as I've mentioned, cost-effectiveness and compactness, but at the same time, by their design, these microscopes are high throughput. They can look at large volumes and large sample areas. And that is a signature of on-chip imaging, because these microscopes that I'll be sharing for the next 10 minutes or so, they are unit magnification microscopes. They are 1x, so to speak, which means the active area of the sensor is equal to the field of view. If you open up one of your cell phone sensors, CMOS imagers, you'll typically see something like half a centimeter by half a centimeter active area, so 25, 30 millimeters square. That is the area, that's the active area of the sensor, but that's the area that we can look at specimen. That's why these are high throughput microscopes, and because of holography, they're highly sensitive. And to the level where we can routinely see sub 50 nanometer particles with these microscopes across 20, 30 millimeters square. So it's opening up new opportunities even at the nanoscale. And the final thing is, these are tolerant to misalignments because we want them to work as telemedicine microscopes, and that's why they're not difficult to align. And even if you drop them to the floor, they would be working fine. On-chip imaging is a general theme in our lab. It has implications for telemedicine, mostly because of CMOS imaging and webcams and cell phones and all the variable computers. However, if you were to start using CCDs that we don't have in our cell phones, but we have in some of our digital cameras, then you can create non-traditional imaging systems for fluorescence and bright field, as shown in these pictures here, to look at this time significantly larger areas, because CCDs in general have larger active areas than CMOS imagers by maybe an order of magnitude sometimes. That's why if you were to design an on-chip imager based on CCDs, you would be looking at maybe a 20 centimeters square active area, 20 centimeters square field of view. I'll come back to this slide maybe midway through my presentation and switch from CMOS to CCD to highlight what you can do with this platform, for which the sensor is just the end component. It can be CMOS or CCD. So to briefly wrap up this introduction, whether it's running on a cell phone using the CMOS imager of the cell phone with a simple light-emitting diode, or a standalone device which also uses a cell phone CMOS imager taken out of the cell phone using a USB-powered interface, or using a high-end CCD. All of these instruments, imaging systems, rely on lens-free inline holography on a chip, where the magnification is unit, it's 1x, and the active area of the sensor is equivalent to your field of view. But it's not traditional holography in the sense that it's not using coherent sources. It's not using a laser. It's actually using light-emitting diodes. Typical bandwidths that we use are a few nanometers to 10, 20 nanometers. as well as we don't have spatial coherence. So the geometry is interesting in the sense that the specimen is placed, the specimen plane is placed very close to the sensor area. This detector area is a CMOS plane, let's assume. And the typical gap between the sensor and the specimen is around a millimeter or so, or sub-millimeter. That's why it's 1x, and that's why the active area is equivalent to the field of view. But the illumination is incoherent. It's actually partially coherent, but you can assume it's entirely incoherent. So it's quasi-monochromatic, something like 10 nanometers bandwidth, let's say. By the time that the light is filtered by this aperture, which is quite large in our case, because this diameter of the aperture that we typically use is on the order of 50 to 100 micrometers. So it's easy to align. You take an LED and place a pinhole, and that would be sufficiently high power for whatever we want to image. And this distance here, which is denoted by Z1, is the tube length here. So this tube length is a few centimeters, as you can see, and that's the distance with which we create partially coherent beams spatially. Which means if you were to, for example, look at the coherence of the beam hitting this plane, you would see that it has a partially coherent beam diameter, typically less than a millimeter in diameter. It doesn't hurt us because of the unique geometry where diffraction between the specimen and sensor occurs with very small distances on the order of sub-millimeters. So this system is, as I've been highlighting, is working based on partially coherent illumination, both spatially and temporally. So there are a few advantages and differences compared to highly coherent illumination forms. First advantage is that by using partially coherent or incoherent sources, we eliminate some of the important noise terms, one of which is speckle. So because of the fact that different parts of the specimen are not coherent to each other, the scattering functions, the scattering fields coming from different parts of the specimen cannot directly interfere with each other. That means we have less speckle and much less multiple reflection interference type of terms. All of those small interference terms that you would normally have with a laser illumination are eliminated. And in addition to that, because we're not so hungry for spatial coherence, you do not need to work with submicron apertures. Traditional holography is very precisely demanding coherence. That's why this aperture diameter would normally be quite small for having very nice spherical and coherent beams. Fortunately for us, we do not work with these tiny apertures because our demand for spatial coherence is not that much. That's why this can be very large. It's also good because we do not need much alignment. If you were to have a submicron aperture there, it would have two major issues. First, light penetration, light throughput through the submicron aperture would be very small. You would need to have a very nice alignment, maybe with some optics to focus light. Now there's no optics. You have butt coupling, literally, between your light source, LED, and the aperture. That makes it easy to align and easy to operate without, again, realignment issues. So in terms of the other element that you need to be worried about, there is also a temporal coherence issue. But before I come to that point, I'd like to mention that for example, in this geometry, this is the distance which gives you partial spatial coherence. But if you were to look at what you get at the raw image from one of these sensors, this was actually a 5 megapixel imager, and this is where you load your specimen. This is a raw hologram that you would get. The scale bar here is a millimeter because, again, this is something like 24 millimeters square active area. This is the area with which you capture raw holograms. These are holograms because the scattered field from each one of these elements that make up of the image is creating these spherical waves as a function of scattering potential of the object. And there is some background light which is highlighted here with the red beam, and they interfere, giving you an inline hologram. Okay, and that inline hologram demands spatial coherence for reconstruction. But again, everything is partial here, and it doesn't hurt us because the diffraction of this spherical beam for a point scatterer is very little. So to speak, you only need spatial coherence across a smaller area, and that's why partial coherence would work. depending on the gap between the sensor and the scattering element, you can actually even reduce this gap between the light source and the active area further. And you can even make this like smaller in terms of the final length. And at the end, you get something like this. These are holograms, and the signature of the hologram is evident from these oscillations. This is essentially the oscillation of the scattering wave with respect to the background, encoding the phase information into intensity. But the nice thing is that, for example, this field of view is not spatially coherent with respect to that field of view, or the neighboring cells in here, which means they do not crosstalk, which is quite important, because crosstalk, which means if there are two scattering elements within your field of view, each of which give you some sort of a scattering field, if they interfere, this is not useful information. As far as holography is concerned, cross interference among scattering elements of a specimen is noise. We actually ignore it entirely, assuming that it's weak compared to the true heterodyne interference term. That's why this cross interference being partially mitigated here is also quite important. In a sense, you can think of it as a coherence gate, where you reject, through the finite size of the coherence gate, some of the other scattering potentials that would normally create noise for your true holograms. And the second thing that is important to consider is the finite bandwidth of your sources. So spatial coherence is important, and you need to engineer your distances, diameter of the pinhole, and the distance between the pinhole to sensor versus the distance between the specimen to sensor. All of these are important for especially making use of your imager as high resolution as possible. But in addition to that, you need to be also worried about temporal coherence problems, because they're independent, and this one is dictated by the bandwidth of your source. Since we're not using lasers, this has to be carefully adjusted. We're using typically light-emitting diodes, which have broad bandwidths, which means at every scattering point, the diffraction here will occur with different wavelengths, and the holograms will start to be washed away, meaning that some of the fringes that correspond to higher numerical apertures would be washed away if you were to have many of these wavelengths present at the same time in your illumination source. That's essentially the intuition behind spatial temporal coherence length. Another way of looking at it is, at a given bandwidth for a central wavelength of something, let's say 500 nanometers, by having a certain bandwidth, by having many of these wavelengths superimposed, you're having a temporal coherence length, which means some of these scattering rays, oblique rays, would not have the temporal coherence to interfere with the background wave, which means those two dashed rays would not be able to interfere if you were to make delta lambda large and large. That would impose a certain numerical aperture problem, because some of these fringes outside from the central point of the scattering element would be washing away. So to mitigate this with a finite bandwidth, you need to actually make this gap between the scattering element and the sensor small. If you make that, then these can still interfere with a finite bandwidth. So that's our trick. Essentially, unit magnification, by placing the specimen very close to the sensor array, is helping us in many ways. It helps us with spatial coherence not being a problem, temporal coherence with a finite delta lambda not being a big problem, and giving us a large field of view that directly scales with the active area. So far, it is win, win, win. But there's a trade-off. And the trade-off is, this kind of a geometry, even though you take care of the finite bandwidth, you take care of the finite spatial coherence diameter, you will be suffering from pixelation. Because by placing this closer to the sensor, now the sensor pixels would be washing away some of these interference terms. I'll come back to that point in the next few minutes. But essentially, by using large bandwidths, we're not suffering in terms of resolution yet, because of the fact that we place the specimen very close to the sensor. But there will be pixelation type of problems that will be on our way for getting to the high resolution. I'll handle those later when we come to pixelation and what it does.
Two questions. So these lambdas with delta lambda, what is typically the range for that L? Because it seems to be around, I don't know, 50, 100 microns, something like that. And the second question is, basically you characterize your temporal coherence with the standard. How do you characterize in general? I don't know, the spatial invariance of the source.
So this L is a path length difference between this beam and that beam. So by placing the specimen around a millimeter or a sub-millimeter, if you were to take any LAD, which has, let's say, a central wavelength of 0.5 microns, and let's say 10 microns, you can still have almost, for a large numerical aperture, almost up to 0.6, 0.7, this condition satisfied, meaning that the path length difference for the highest ray, highest angle ray, and the background, this path length difference is the path length difference between this one, this black, and the red, still would be satisfied because we are placing the specimen very close. If you're working with broader and broader bandwidth sources like delta lambda, you can actually push this point closer to the sensor and still satisfy the same condition of interference for a finite delta lambda. So this is how you can have an engineering knob there to fine-tune satisfaction of this coherence. The NA is coming from this angle over here, which means for a certain high NA that you want to capture the interference of which, then you need to consider a certain angle and find the path length difference of that angle with respect to the straight ray. That determines for a certain numerical aperture that you want to have the interference for. That determines the delta lambda, so delta L that you need. Okay, it's independent of temporal coherence. It's a certain delta L requirement based on where you place your scattering element, and that delta L will dictate what kind of sources you need. And accordingly, if you're using a broader band source, you need to chop it with a filter or whatever so that you have a sufficient delta lambda to say that if you ignore pixelation, which I'll come back later, let's say the pixels are never on your way, what would it be the requirement on the source bandwidth for a certain numerical aperture to be present in your hologram? So that's essentially how you calculate, well, based on my LAD, based on my bandwidth, based on this gap between the specimen and the sensor, what kind of NAs, if everything went right, you could be capturing on this geometry. This is temporal coherence. In terms of spatial coherence, you will be worried about if there is a scattering element here and scattering element there, and the sources are above us. What would it be the coherence diameter of your illumination so that the scattering field from this would be still able to interfere with the scattering field from this? And essentially, the diameter that I'm referring to, not not with respect to the temporal coherence, but the spatial coherence, is the diameter by which you start to increase the distance between these two scattering elements, and you still can see interference between those two. And after a while, you will see reduced interference fringes. You will say they're partially coherent, and after a while, you won't see any. So that's typically sub-millimeter. Yeah. So, and you can fine-tune it by fine-tuning this length here. The more this length is, you increase it. The smaller you make this, you increase it. So it's all about assuming a certain wavelength. By playing with this diameter and length, you can actually fine-tune it as you like.
Does it mean that at a time you can only look at 1 millimeter, like everything?
No. This is only for the holograms, for the hologram's numerical aperture. So you're recording a hologram and you're trying to understand if it has sufficient interference. But regardless of the diameter of coherence, this would be satisfied. For example, this is irrespective of your spatial coherence diameter, this is what you get. What you will be changing is the fringe visibility, so which means the reconstruction. For example, this is a certain hologram. It has certain numerical aperture to it, certain resolution. But if you were to play with the aperture here to make it broader, larger, you would be degrading the spatial coherence, and all of a sudden some of these fringes will be lost. But at the end, you would still get the same field of view, and the reconstructions would lose their resolution after a while. So essentially, there's a trade-off if you were to make this aperture larger. Typically, we work with 50 to 100 micron apertures, and this gap is a few centimeters, which give us almost diffraction limit resolution, except the pixelation. Pixelation is an issue. I'll come back to that later on. So, like any other inline holography scheme, you need to reconstruct, because these are inline holograms, not like off-axis, so you have some of these twin image artifacts coming in. And for reconstructing an inline hologram, there are different ways of doing it. And we use several different approaches, and they all almost perform the same. In our reconstructions, we use iterative methods, meaning that these are not analytical solutions. These are iterative methods that we're trying to predict the missing phase information. So one way of looking at this twin image problem is essentially that every time you focus a hologram to the real image plane, you have also a virtual image diffraction on the same plane. So you have the focused scattering element, but you also have around it a defocused image because of this twin image or its diffraction. So you can look at image reconstruction in holography as a means to eliminate this twin image problem. And there are various different ways of doing it by going back and forth between the virtual image plane and real image plane, or hologram and the real image plane, enforcing certain conditions. So one basic approach to look at this is actually phase recovery. So you have a hologram or its amplitude, and this is missing phase. So this is an amplitude of a field, and it misses this phase information. If you have the phase and amplitude, you can actually have a complex wave, which you can time reverse. You can take a complex wave and essentially travel it to any plane with respect to your specimen. To recover this phase, what we do is we go back and forth between the object plane and the hologram plane. So this is a loop, which is a iteration based on FFTs. Typically, less than 20 iterations, you converge to the phase. For convergence here, we every time we iterate here, let's say initially you assume a certain phase, a random phase. You go to essentially the object plane, and because of the incorrect estimation of the phase, the object is not satisfying a certain support. It's leaking its energy outside of your field of view. You can enforce the field of view constraint and perturb what you guessed. If you go back to the hologram plane again, you will get two different quantities. One, an intensity or amplitude, and one phase. Intensity, I do not care what the loop predicted because I've measured it. So you have a measurement coming from your system. You enforce the measurement and keep the phase. Now you have a better estimate. You go to the same loop again, and at the end of each cycle, you will have two different quantities, amplitude and phase. You don't care about the amplitudes. You only try to retain the phase and enforce the measurement. This is also called as error reduction algorithm. So you guess and you correct it. And it's based on essentially a support constraint. Later on, I'll show you how this can be more sophisticated without any object constraint, without any field of view constraint. It can get better convergence, especially for dense specimen. And that's whenever I talk about multi-height imaging based on inline holography, I'll come back to this phase recovery loop and then tell you how we can do this actually in a more robust way. But in a simplistic manner, this is what's happening, and you can look at this entire inline holographic reconstruction scheme as a phase retrieval problem. Once you have that phase, you can actually, again, go back to the images. So far, I've briefly talked about coherence issues, temporal coherence and spatial coherence, and how these are partially tuned to give you a hologram that essentially still captures whatever you need in terms of resolution. I've ignored pixelation, but even with today's or previous generations cell phones, you get actually a very good resolution. So whether it's working on a CMOS imager using the cell phone's interface, or a standalone CMOS taken from a cell phone or a CCD, all of these platforms are based on 1x inline on-chip holography, and they're working based on partially coherent illumination. Typical sensor pixel sizes that you have in your cell phones is on the order of 2 microns in the previous generation. Like a couple of years ago, most of your cell phones had 2 micrometers. These days we have around 1.5 micron pixel size. So let's ignore pixelation for the time being, and using a simple light source like this coming from an LED, you actually capture these holograms, synthesize phase. Once you have the phase, you go back to the image plane. These are platelets. Each one of these is around 2 to 3 micrometers. These are some white blood cells. This is, for example, a granulocyte. Every time you reconstruct, you get an amplitude and a phase, and these are some comparison images. These initial results are lower resolution, meaning that they are mostly pixelated in the hologram domain because of the finite pixel size, which is, in this case, the pixel size was 2.2 microns. So it's one of those old sensors, at least 6 years old. But still, you get some resolution to the level where the resolution was equivalent to around a 10x objective length. Even with this simple case, you can be using it for certain applications. For example, one thing that we push this platform with its lower resolution platform, with the pixelation being in our way, you can actually look at CD4, CD8 lymphocytes, and this is an important problem for HIV positive patients. So each one of these spots that you see on this chip is actually capturing specifically and sensitively certain populations of white blood cells from HIV positive patients. This is actually an HIV positive patient blood being run. And these are antibody islands. Each one of these circular spots is a printed antibody. In this case, 2 different types, anti-CD4 and anti-CD8. So that when you run whole blood assay, you will selectively and specifically capture at different parts of your chip these CD4 or CD8 lymphocytes. And once you reconstruct them, you can count them to give you the ratio of CD4 and CD8 lymphocyte. This is a problem where you need a labeling scheme because the nature differences between a CD4 and CD8 is not enough for optical microscopy, no matter what the resolution is, to be able to differentiate. That's why you do spatial multiplexing. So for example, this spot is a CD4 and this one is a CD8, and that's how you know what you've measured. If you zoom in, you'd be seeing CD4s are more dense than CD8s. This is normal. A healthy person would have this kind of a signature. But once HIV kicks in, you would see a reduction in density of CD4 spots. And that's how you can use this, for example, to understand the depletion of CD4 due to HIV. So if your viral load, for example, is above a certain number, you would have a significant reduction of CD4 selectively compared to CD8s.
I'm not sure how you're differentiating CD4 from CD8.
This is based on a surface that has antibodies on it. So it has, for example, these spots have anti-CD4. These spots have anti-CD8. And they're multiplexed in the same array. So when you flush it, they specifically capture them.
And do you know that some specific area is the...
Yes. 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 So you have a printer which prints locally, and then you have an array, and you know which parts are CD4 covered and which parts are CD8. And typically you average over many of these spots so that you also take care of non-uniformities in the flow of the microfluidic device to average the count of CD4s to CD8. In our case, the ratio of these give us a number. If that number drops below a certain threshold, you are supposed to start antiretroviral therapy. Indirect measure of viral load, essentially. So everything that I've shown you so far is using a single light emitting diode here. And it's using a chip CMOS imager that you place on the top, and 1x inline holograms. The resolution of this system is having a numerical aperture of around 0.1 to 0.2, something around 1.5 to 2 micrometer resolution. But 1x configuration and a field of view is a major advantage. So you can think of all these numbers except the field of view typical for a 10x objective lens. Resolution numerical aperture is typical of a 10x objective lens. But the field of view is the advantage here because a typical objective lens with 10x would be looking at a few millimeters square, maybe 1 to maybe if it's a high-end microscope objective, maybe a 4 millimeters square. So you have an advantage coming from the field of view and depth of field. However, the numerical aperture is not as high as we would like. Mostly this is because of pixelation. Essentially, the finite pixel size here, which is in this case 2 microns, roughly speaking, is washing away some of the fringes that are coming from the diffraction patterns. To mitigate that, we've actually borrowed some tricks from super resolution literature. Super resolution is a term that is used for fluorescence microscopy to beat the diffraction limit of light. Especially over the last 15 years, 20 years, it's been heavily used by fluorescence microscopy, like techniques like STORM, PALM, have used super resolution as a keyword to emphasize that they are beating the diffraction limit of light. In fact, super resolution is much before fluorescence microscopy utilized it. It's used in photography literature. Super resolution means taking a low NA imaging system and creating a synthetic aperture out of it to digitally synthesize a higher numerical aperture out of this lower numerical aperture imaging system. So super resolution essentially means, even for photography, improving the resolution of the native imaging system. So our super resolution is that original use of super resolution. So there's nothing fluorescence yet here, and that's why do not confuse it with, for example, PALM or STORM type of super resolution techniques. However, this is the correct term because it's being used before fluorescence literature. So the design of the super resolution lens-free microscope is a little bit more advanced in terms of its hardware, but still very cost effective and lightweight. For example, this design, which is a couple of years old now, is less than 150 grams. Still, it's very lightweight, field portable, and as you can see, very easy to carry around. What you have inside is, instead of a single LED, we have some 20 LEDs now. So it's very still cost effective because each LED is a few cents. What happens here is, as before, you load your specimen in front of a CMOS imager by a disposable tray as shown here. And at a given time, only one of the LEDs is on. So these LEDs are butt coupled to multimode fibers. So each one of these white-looking strings is a fiber optic cable, 100 micron core size, very large. It mimics the pinhole. And they're butt coupled to a bunch of LEDs. And these LEDs are controlled digitally. So there's nothing mechanically moving here. Everything is digital image capture by turning on LEDs one by one. At a given time, you capture an inline hologram as before by a certain light emitting diode on here. This is the red one here that is on. You capture as before a hologram, but that's lower resolution because of mostly pixelation. But what we do is we shift the light source by digitally turning on different combinations of LEDs at a given time. And the end result of that for a fixed specimen is holograms start to shift at the subpixel level. It's equivalent to sun moving as from, for example, noon position to 2 p.m. position. You would see shifts in shadows. It's exactly the same process, except we control the sun here to give us subpixel shifted holograms of the same static scene. That enables us to synthesize digitally pixel sizes that are much smaller than physical pixel size of the sensor. It's the same trick that is borrowed from photography literature. Security cameras have the same built-in pixel super resolutions, advanced ones, where if you, for example, capture a movie where every frame of the movie is lower resolution because you're far away from the imaging system, let's say, but 10, 15 of these frames can be put together to synthesize a much higher resolution image of the same scene. This is called specifically pixel super resolution, and the equivalent of this is you take a pixel and digitally divide it into smaller chunks. For example, let's say if your pixel is 1500 nanometers, you divide it into 10 by 10 to create a much smaller pixel size effectively. For holograms, the effect of this is bringing back the oscillations that are normally washed away. This is the same inline geometry of an object. You get these nice fringes corresponding to a certain numerical aperture, let's say 0.2 in this case. But after a while, even if there is some hologram here, your pixels can't sample it. That's why you washed away some of these higher oscillations. Only after pixel super resolution you can resolve these, and these correspond to higher numerical apertures. Which means if you were to reconstruct a lower resolution hologram, some of these finer features will be lost away, but only after pixel super resolution. You can get in amplitude and phase these grating lines here that are normally, again, washed away. This is the corresponding image. These are, relatively speaking, lower resolution images because of the same Moore's curve that I've shown. The sensors are improving themselves rapidly, every 2 years increasing their space bandwidth product, and that helps us to improve these images drastically every other year almost. Using, for example, a state-of-the-art CMOS imager. This is one of the sensors that you can buy in your iPhones. iPhone 4, I believe, has this sensor. It is a nice CMOS imager which has a pixel size of 1.1 micrometers, and it has around 10 megapixels. The active area of this sensor is around 20 millimeters square. So now this image, after pixel super resolution, it has around 1 billion useful pixels. So it's around a gigapixel. And if you were to zoom into different parts here, you can resolve, in this case, around 225 nanometer grating lines written by focused ion beam milling. So the numerical aperture of this system in this initial work, which was around 2012, was around 0.9, but now this is a diffraction limit. So by using oil immersion tricks, you can actually push the resolution here up to the numerical aperture of 1. So it's almost diffraction limited across such a large field of view, giving you around 1 billion pixels. Why are we so much obsessed with field of view and having billion useful pixels? What is the use for that? A lot of the times for especially pathologic investigation of specimen, you're looking at rare events. You're looking at, even if you're dying, for example, from malaria, the infection rate for red blood cells will be very low. The peristhemia is typically less than 1%, most often less than 0.5%. That is why you need to look at large areas, all the way from one part of the diagonal to the other. You need to look at, in this case, this is a thin smear. You need to look at red blood cells and to see if, for example, a parasite would be invading the cell. And this process of parasite invasion is actually quite rare, as I've said. So you need to look at many of these power field of views. Typical objective lens would be looking at these tiny circles. And in the case of malaria, there are two important uses of a microscope for looking at a malaria-infected patient's blood. First one is for diagnosis. By looking at the parasite signature, for example, this is a healthy red blood cell. These are healthy red blood cells, but if parasites kicks in, infects the blood of the patient, every now and then you would get this purple-looking Ginza-stained parasite invading the cell. The same thing looks like this in the phase channel of the same microscope. And again, this process is quite rare. So for diagnostic purposes, you may want to look at under thin or thick smears parasite signatures. In addition to that, there's also importance for looking at evaluation of the parasite, for tracking how the patient's, for example, therapy is doing. In that regard, even if you know the patient is positive, understanding the percentage of infection per red blood cell is important, because a lot of the times you have drug resistance. And once you have drug resistance, the peristhemia does not drop. And so you need to know exactly what's going on to treat the patient. That's where microscopy is more useful than some of these other rapid diagnostic tests, which can give you a yes or no decision, but at the same time, no information about parasite rate in your blood. And this is a typical field of view of these microscopes, as I've shown again, but now you can push the resolution limits through pixel super resolution. A state-of-the-art platform for the same design is as shown here, which is now having some more additional control knobs to push for resolution and at the same time performance. In this case, this is the same super resolution engine. These are fiber optic cables, which give you this super resolution through shifts at the subpixel level. At the same time, we have some lower resolution color images so that we can synthesize artificially colored images. So the boundaries are super resolved, but now you can also have some color images coming from lower resolution RGB channels. In addition to that, we have a knob here to play with the distance between the specimen and sensor. This is a very rough Z stage, which modulates the distance between the sensor and the CMOS sensor. Sorry, the sample and the CMOS imager. So this modulation essentially is changing the distance between the specimen and the sampling plane. And you don't need to do this in controlled manner. So that's why it's a very inexpensive one. How do we make use of this? We make use of this in our reconstructions to stabilize our reconstruction process. And it's a very simple design here, which modulates essentially just a sensor here. This is a CMOS chip. And in our reconstructions, we make use of it for phase retrieval. I've shown you in the very beginning a slide which talks about phase retrieval. But now instead of going back and forth between the specimen plane and the sensor plane to enforce an object support, we do not deal with that anymore. We just throw a phase to one of these holograms captured by a certain Z2 distance between the specimen and sensor, and essentially move back and forth between different heights. Every time you move forward a complex field, which has your measurement and a guessed phase here, you will be inconsistent with your measurement in the other plane. That's good because that inconsistency is a result of your incorrect phase guess. But now it gives you an opportunity to correct it. At this plane, you enforce the measured amplitude and retain the phase. Move to the next plane. In this next plane, because you haven't yet converged, you still will have inconsistency because the amplitude here will not match your measurement. So you force the measured amplitude and retain the phase. Typically 1 to 2 full cycles with, let's say, 3-4 heights would converge to a phase for all these holograms, which means you will have independent recovery methods now. You can pick any one of these planes, let's say plane number 2 or plane number 3, whatever, and you can reconstruct it, and they would give you the same result. And that's also a measure of convergence. This is now very robust. Actually, this can routinely now generate even connected tissue reconstruction. This is a PAP smear, Papa Nicolau smear. This is used for cervical cancer screening. And now you're seeing a reconstruction of that over a large field of view. The scale bar is the same signature here. These are some reconstructions. Now it has color coming from the color LEDs, and the pixel super resolution is achieved here through a multi-height recovery in a field portable design. So everything that I've shown is acquired with a CMOS imager, and this millimeter scale bar is a signature of that. It's essentially showing you that this is a CMOS imager, because most CMOS sensors have around 20 to 30 millimeters square. But if you were to use some of the other types of optoelectronic sensors like CCDs, all of a sudden you will have a new world in terms of field of view. For example, going from a CMOS to a CCD would make the scale bar go from a millimeter to a centimeter, and you would have, in this case, a very large field of view, around 18 centimeters square, something like 1800 millimeters square, where you can now do a microscopic imaging with around 1.5 gigapixels. And if you want to see, for example, how the raw images look like, these are raw holograms, highly pixelated. Because CCDs have larger field of view, but they also have larger pixels. This sensor has around 6.8 micrometer pixel size, 6.8 micron by 6.8 micron. That's why they look terribly pixelated. After super resolution, you get back these holograms, and once you invert those, you get these sperm images. Each one of these is sub-micron tail of a sperm. And you can understand the power of the system because 6.8 micron by 6.8 micron is sampling under 1x sub-micron tails of these sperms. It's a terrible sampling problem because the sampling period is 13 microns range. And that's where pixel super resolution helps you to even resolve these things that are deeply subpixel. This is also highlighting an important feature of on-chip imaging in the sense that it's independent of the sensor. Your black box, in terms of reconstruction, you can use whatever sensor you like, depending on your resolution field of view combination. If you're hungry for your resolution, if you really want high numerical apertures, you can use a CMOS with the smallest pixel size. That would give you maybe 20, 30 millimeters square field of view. But if you're really after field of view and resolution is secondary for you, then you can go for large pixel size, large area sensors. So this gives you a combination of field of view and resolution, which you can tailor depending on your needs. And one important thing here is the decoupling between those two parameters. Field of view and resolution are decoupled here. That's a fundamental coupling in optics in the sense that any lens-based system would lose field of view if you were to go to higher numerical aperture imaging. So there is a fundamental trade-off between field of view and resolution. It's equivalent to the space bandwidth product of the system. Here, if I were to get, for example, let's say this is a 10 megapixel imager. Next year, if I were to get the same sensor, 20 megapixel, with the same pixel architecture, you would be buying more land with the same resolution and creating an image that is, instead of 30 millimeters square, you'd be looking at maybe a 60 millimeters square area with the same resolutions, so that the resolution and field of view are not tied to each other anymore. And if next year we have a better sensor, which is, let's say, smaller pixel size and more megapixels, then you can improve both resolution and field of view. That's why in my images throughout the beginning, I show different kinds of sensors, and some of those images were looking less high resolution than the other ones. And that's because of this natural evolution of different sensors coming. And every time we have a better sensor, you can improve field of view and or resolution while keeping this other the same, or at least around the same, while significantly improving the other. So this gives us a good way to kind of balance our needs with resolution and field of view kind of question. Sure. So this is again a guess and correct algorithm, error reduction. You can throw a phase in here, and you create with an amplitude a certain complex wave. Once you forward propagate that, you go to another plane. At that plane, you have digitally come up with two different quantities. One of them is an amplitude, and the other one is a phase. Amplitude you don't care because you always have the measurement for that. And you're trying to converge to the phase. Exactly. So you retain the phase saying, well, okay, this is probably a better guess. But I won't guess my amplitudes because I've measured them. And I'm relying on my measurements to kind of convert to the phase. Yes. Yeah. These are giving you, you could have done the same thing by just retaining one and enforcing some object support. But this is better because this is oversampling some of the unknowns for a dense region. So if we're dealing with dense objects where the specimen is coming closer to each other, this retains a better convergence than just one of these planes. Well, this is a unique phase retrieval problem. So analytically, you can look at this as a unique phase retrieval problem. Whether or not you found the optimal, globally optimal point of convergence or not is a question of resolution. Because resolution is going to tell you, well, okay, the phase around this region of interest was probably not optimal, and that's why you lost some resolution. That's why if you look certain objects which create some problems for the field will give us trouble. What do I mean by that? So let's say you have a certain region where the specimen is a little bit three-dimensional, and you have certain scattering elements that block the others. Then it's the same shadowing effect in optical coherence tomography. If you're looking at an optical coherence tomography image, Whenever you have, for example, some highly scattering region, like a stent in your arteries, you immediately see the artifact of that in your OCT image because it creates a shadowing. Because the signal-to-noise ratio for the specimen behind your stent metal is very poorly illuminated. Stent is a great example because it's perfect reflector almost, but the same kind of shadowing artifacts naturally occur for certain tissue types. It's the same here. If you have a difficult object which is three-dimensional and some of the front elements are scattering stronger than the back elements, then you will have what we call cross-scattering interference. And that's a noise term for any kind of imaging system, especially a coherent imaging system. That's where you can't claim to have converged to the global thing because your assumption that the object is composed of point scattering elements is incorrect because those point scattering elements interfere with each other, giving you a field which not necessarily represents the morphology. So what optical microscopy deals with is fields. Coherent, partially coherent, or fully coherent. How it relates to morphology is an unknown thing. It's a chicken-egg problem. And this is very difficult to invert unless you do some tomographic elements to resolve all of that from each other. Even with tomography, there are assumptions that involve. How morphology or a three-dimensional volume of scattering elements create a field is an interesting question, but without knowing the morphology front end, you can't solve this problem. And if you know the morphology, why are you imaging? So that's the chicken and egg problem. This is all partially coherent. This is the illumination coherence requirements have not changed. Yes, this is transmission only. So, for example, this is if the tissue is more than 20 microns, 30 microns connected, it doesn't let light enough pass through. So, this would be good for histopathology, sub 10 micron. But if it's a thick tissue and it's connected, it wouldn't work. This could be good for small animal screening as well. For example, a C. elegans worm, which is like 50 microns thick, could be imaged with this. But if it's a 50 micron C. elegans cake, then it wouldn't work. So you can also do imaging of nanoparticles. In this case, we're making use of some self-assembled lenses here to help us with the scattering potential of very small objects. Now this is an application for detecting extremely small particles, like sub-100 deeply sub-wavelength particles. And the problem with them in a lens-free imaging configuration is because they're deeply sub-wavelength, they do not scatter much. Which means the scattering wave is so weak, especially imagine you're trying to find the scattering of a 50 nanometer, 100 nanometer particle from a distance of a millimeter or half a millimeter without any lenses. So, and there is a huge flux of photons coming around you, which is the inline transmission geometry. This is a very difficult problem for inline geometry because the most of these photons, if you are looking at a deposited particle or let's say some viral particles captured on a chip here, most of these photons are filling up your wells in your imaging system. And the tiniest scattering coming from these nanoparticles will be a small fraction of the photons there. To solve this problem, we're using self-assembly of nano lenses around individual particles. These nano lenses are room temperature stable. They're made out of a polymer, like a plastic polymer, which coats the neighboring area under each particle. And the physics behind this self-assembly is very similar to, for example, forming this shape with two rings. If you take two rings, like wedding rings, and dip them into a soap solution and take them apart, you self-assemble this type of a thin membrane of soap. This is actually a catenoid. It's a minimal surface. A catenoid is something that you take a catenary, so like the chain of a catenary, and you revolve it around the axis. You form this beautiful shape, which is known as a catenoid. So if you cut this catenoid in half and shrink the dimensions to nanoscale, that's exactly what forms around each particle. So these are nano lenses that are surrounding each particle. The end result of that is an increase in the scattering potential. But this is not a selective process. Whatever is on the surface, you form these nano lenses so that you can count them. So the question is, to bring specificity to this platform, you need to functionalize the surface. That's why the example that I gave earlier for CD4 versus CD8 is the way to bring in specificity so that the particles that are on this gloss is specifically captured. So the same field of view, it's the same CMOS 1x configurations. If you zoom in after a while, you would be zooming in to the holograms. In this case, the holograms are not there to your bare eye, but they are there. It's very difficult to imagine what you see here. However, only if you reconstruct, you will be seeing essentially these sub-100 nanometer particles coming from, in this case, the SEM is our comparison. This is, for example, a 70 nanometer particle, which is reconstructed across the same field of view. And again, you can use this for viral load measurements with the same idea of you can functionalize the surface, capture a specific viral particle based on antibody surrounding the capsid of the virus particle, and then you can now look at the phase or amplitude images for looking at individual viruses. So the advantage here is field portable, single virus particle level detection over large fields of view, which means you can have a good dynamic range for example, viral load measurements. This was a C. elegans experiment that I briefly mentioned. You can do tomographic imaging of C. elegans by using pixel super resolution, but at the same time multi-angle. This is like a dual axis limited angle tomography. Limited angle because this range of angles would create some problems for CMOS. That's why we do not enjoy the very oblique rays. And to make up for this limited angle, which is plus minus 50 degrees roughly speaking, we also do orthogonal axis, so we can have better images. For example, this is a movie which shows tomographic imaging of a large volume with around 3 micron axial scanning. And this is a C. elegans that is being reconstructed now. So this is the Z scanning, and this part of the animal is now getting in focus. Soon this part will also. This is slightly tilted. The worm was tilted. So these are relatively old results, as you can see, at least 3 years old now. That's why the sensors used in these reconstructions were 3 generations before. And now if you were to do the same experiment with some of the recent ones, you would get better resolution. And that's the nice thing about this platform. So I'll now finish with some other things that you can do with the same platform, but this time for imaging dynamic events. Previously, I was mostly concerned with imaging of static objects. These were things that you fixed, and after imaging, you would be disposing for, let's say, diagnostic purposes like bloods or other kinds of pathology samples. But now we're interested in looking at motion and sampling motion, and in this case, looking at microswimmer motion. We'll be looking at an on-chip, holographic, and partially coherent on-chip imager, where the goal here now is to track the motion of sperms in 3 dimensions with submicron tracking accuracy in 3D. So I want to literally understand how the sperm is moving around in 3 dimensions with a large volume. So not just a few of them, but I'd like to track them in thousands. So at the end, I want to create a pool like this, a giant pool 0.5 millimeter in depth or so, where each one of these colorful things is a single sperm's trajectory across maybe 10, 12 seconds. And more if need be, but this is what I am interested in. How do they move continuously across a giant volume at the submicron level? For this, the geometry is a little bit different in the sense that it's still in line, and I'm capturing holographic shadows, but now there are 2 shadows per sperm at a given time. It's like playing soccer in during dark, so that per player, you would have many shadows. But now we have two. One vertical and one oblique. So per sperm head, you will have two shadows, which are oversampled in the sense that the frame rate of this imager will be something like 150, maybe 200 frames per second, so that we can sample the fine motion. But the color is changing as well, so one of them is a red and the other one is a blue LED. The reason for that is to be able to differentiate the reconstructions for the vertical and oblique projections, so that we can actually pinpoint to the three-dimensional location of the sperm. If you look at one of the zoomed in raw data from a smaller field of view, this is what you get. These are holograms and these are sperms moving, but it's very difficult to understand what's going on because there are many sperms, obviously, but also there are two holograms per sperm. So only if you take this data and process it at the correct wavelength angle combinations, you can actually pinpoint to the sperm head. If you were to select incorrect wavelength and angle combination, you would wash away and you wouldn't be able to track. You'd be only tracking artifacts of the focused objects. If you were to combine these two, you localize the three-dimensional position. Not only the XY position of the sperm, which is easy to do with only a single vertical source, but the most important thing here is depth. For depth, a combination of these will give us not only XY, but Z localization. And out of this, you can actually track all of the sperms, not only across this field of view, but across the entire sensor area. So this is one of those, which is tracked here across a second. Now, this is a second of a motion of a human sperm, and this is conducting a helix. The front view here is the straightened trajectory of this sperm, and it's like a diameter of 2 to 3 micrometers, and the time is encoded here with color. This is a very difficult to capture movie because the sperm is moving out of focus, and that's where holography has the advantage, because holography does not care about the depth of field. We find the depth of field essentially by reconstruction of the raw holograms. And at the same time, obviously, this is a very tight motion. This is one of the first movies that show a three-dimensional helix for a human sperm. And that's the reason why high throughput was very important, because this only happens 4 to 5% of the time. So this in vitro helical motion of the human sperm is a 4 to 5% of the time event. This is another one. This is even more rare. It's a hyperactivated human sperm. If you look at the front view, it's now more irregular, larger. It has more energy to spend, and it's exactly doing the same kind of helical motion. So with this platform, we've looked into, again, thousands of sperms. And each time you conduct an experiment, you can run it for a few hours, so you really collect a lot of data. And these are some of the results that you get. There are more than 24,000 dots in here to characterize curvilinear velocity, straight velocity, rotation speeds of everything. Out of these motile sperms, there are 24,000 individual trajectories here. Only around 1,000 of them were helical. So the in vitro rate for helix for human sperm is around 4 or 5%. But interesting thing is that there's a broken symmetry between right-handed versus left-handed ones. 90% of the helical sperms are actually conducting a right-handed motion. Only 10% was actually left-handed. So 96 out of 24,000 was what it takes to find statistics about left-handed. And that's the advantage for high throughput on-chip imaging, because now it takes you maybe a few days of experiments to get to these large numbers and isolate maybe 96 of those. Significance of this, we do not know. So why is there a broken symmetry? We do not know. But it's a platform where you can actually do interesting high throughput studies where different parts of this chip can be divided into smaller subcompartments where you can actually look at, for example, how the statistics change from one part where you put certain chemicals to the other. And that's why high throughput studies of different attractants, different chemical drugs, different external stimuli like heat could be studied on the same platform. Since then, actually, we discovered some new motion in the form of chiral ribbons. So this is a motion that no microswimmer have ever been reported to conduct. So it's in the form of a ribbon. So the sperm head is conducting a sinusoidal motion across a plane. So it's like doing a regular nice sine motion, left and right. But the plane itself is twisting in two ways, either in the form of a helical ribbon like this, and in the other case, a twisted ribbon. So these are interesting observations that we came up with in horse sperm. This is a horse sperm that is now conducting a 3D motion for across 4 seconds. And you're looking at the 3D motion here, and this is the front view. It's planar, but the plane is twisting in the form of a helical ribbon. I'll fast forward this. So now this gives you a better perspective about how the ribbon foils in the form of, again, an interesting mathematical construct. This is a perfectly regular motion, which is surprisingly beautiful in this perspective, especially. But it's we do not know the significance of this, but it's one of those things where I think the throughput can help us to better identify. This is another one, which is a twisted ribbon. So it's now conducting this type of a motion where the ribbon itself is twisting like one of these shapes here, and the motion is still sinusoidal. This happens to be also a minimal surface. So this is a helicoid. Mathematically, it's a helicoid. It also has zero net curvature, just like a catenoid is. Those are interesting things to understand, actually, why or under what conditions the sperms prefer this type of a motion compared to some other. So, and these are experimental results, and these are some fitted mathematical constructs that exactly match what you observe here. So in that regard, it's quite precise what the molecular machinery enables for the sperm head to move. So to summarize, I've described how computation can simplify microscopy and sensing tools, instruments, through the use of some of these smartphones or smartphone components like CMOS imagers to create new instruments for applications in telemedicine, mobile health, point of care. At the same time, fundamentally helping us with some of the difficult imaging, biomedical imaging tasks. I've shared some of those results with especially sperm imaging. This would be useful for field portable tests, for field use, resource poor settings, but at the same time, it may have implications for developing countries, for democratization of measurement science. What I mean by that is researchers and educators in developing countries would also have, through these kinds of computational instruments, cost-effective but powerful instruments to run some of those experiments that require normally a large infrastructure or maintenance. And that's where I think beyond just telemedicine, beyond field applications, there are also other kinds of important applications for democratization of biomedical science in general and its training, practice, and education. With this, I'd like to conclude and thank you.
Thank you very much for a very interesting talk. Maybe one or two quick questions, and we'll ask more during the break, since we're running late a little bit. 1, 2, okay.
Okay, I have a general question. So you talked a lot about telemedicine, but can your reconstruction algorithms, do those run on the cell phones, or are those on a separate computer? And if they're on a separate computer, how do you envision incorporating them into the diagnostic process?
So, depends on the modality, but for example, for tomography or for super resolution, they use separate PCs. But that's never a problem for computation is never a problem for us, because the trend that we have with mobile phones is amazingly interesting and rich in terms of looking at graphics. So today we have graphics processing units in smartphones, many core, actually 4 core appearing soon, and that gives us exactly what we need for dividing a field of view into smaller chunks and then giving it to different cores of the GPU installed on cell phones. So reconstruction is never an issue for what we do, especially with this current status. But at the worst case, you can do reconstruction with a cluster of GPUs off the site, even without a laptop, where you just send a compressed image. Holography is also good for compression. We've done this study. We took our holograms and compressed them. 4 bits, so just to give you an idea, 1 millimeter by 1 millimeter field of view, which is typical 10x field of view, can be compressed with the raw hologram to around 100 kilobytes. And that's what you need to send if you want to reconstruct that field of view. So in that regard, holography is easy to compress relatively to direct sampling. The idea is because you distribute a single scattering function into many pixels. So in that regard, it's much better handling pixel level distortions and even dead pixels compared to direct imaging based on the same focal plane array. Imagine, for example, there's a scattering element, and you were unlucky that your dead pixel of your CMOS imager was around it. It's irrecoverable loss of information. For us, it doesn't matter because that single dead pixel would only be sampling 1/100th of the information, and we don't care. As a matter of fact, we throw away a lot of the information when we use color sensors. For example, a color RGB sensor has blue pixels, 1/4, red pixels, 1/4, and half green pixels. When we use only green illumination, red and blue, we don't care about them. So we throw away half of them. That becomes important when you do color imaging. Then you can turn on the red and make use of red LED, make use of red pixels, and then have interesting combinations. But that's another advantage of holography in terms of computation off the site, because it's compressible highly.
So I noticed in a lot of the full field of view holograms, you have a slowly varying ripple effect across the entire image. And I'm wondering, what is the origin of that?
That doesn't hurt us because I'm showing you an image with 1 millimeter scale bar. The microscale features are very small. So if you were to zoom in, you would see no gradient. So the gradient is only a problem if you look at this image, right? This is where you see it, but this is 5 millimeters. Sorry. So this is 5 millimeters.
Are you talking about these?
I think he's talking about, yeah, I think those. Those are coming from the multiple reflection from the glass slides. So it's a microfluidic device essentially where there's a floor and there's a ceiling, and they have some finite thickness. So this is kind of like the slow variation across that, which is because of the fact that across 5 millimeter, these are like potato chips, right? A glass slide is like a potato chip. It just bends a little bit. And all of those imperfections for thin glass slides give you this slow thing. However, I mean, if you look at this region, for example, if you zoom in, it's uniform across each cell line.
Great. With this, let's thank our speaker one more time.